Hi friends! Okay, so today we're going to be talking about equivalence relations. Okay, so we need to start with a set X. So in a set X, we have an equivalence relation, and normally when we talk about equivalence relations in general, what we'll do is we'll refer to them as like this. So I don't think it's called a tilde. I think it's only called a tilde when it's like above a letter. But yeah, my one of my professors in undergrad always called it a twiddle, and so I've kind of adopted that. So in a set X, we have an equivalence relation, say twiddle is what we'll call it, on elements in X if the following statements are true, or always true. Okay, so what are these statements? So the first statement, so I normally call these like I, and I. Why I do that is because often it's a lot easier to just refer to, part I or part II or something instead of talking about 1, 2, or 3. Because a lot of times in a problem, we're actually using numbers, right? But we're probably not using like 3 I's in a row in our problem. You know what I'm saying? Or maybe even you're doing a homework set. I don't know. I digress. But anyway, part I is the reflexivity. Oh no, I didn't say that right. Okay, so that's the name of this property. And how it's stated is if there's an element A in X, then A twiddles A. Okay, so every element twiddles itself. Okay. Part 2, symmetry. Okay, so for a relation to have symmetry, if A twiddles B, then B twiddles A. Also, so sometimes students get a little bit confused on this. So that means that A and B are elements of X. You can't have, since the relation is defined on X, you can't talk about like let's say 2 is not an X. You can't talk about 2 twiddling something because 2 is not an X. The relation isn't defined on 2. So you can't say 2 does or does not twiddle something. Okay? All right. And so our third property is called transitivity. So you want to make sure every relation has is reflexive, symmetric, and transitive before you can call it an equivalence relation. Okay, so here's this one. So if A twiddles B and B twiddles C, then A twiddles, okay? So if the if part is true, then the then part must be true. So there's another way to think about it. And if this is already kind of making sense to you, that's fine to just stick with this. Some people, this makes more sense. Some people, the second definition I'm going to give you makes more sense. Either way, though, is totally fine. Okay, so they're equivalent as definitions, but some people it might make more sense. So my other way. Okay, so another way to say this is we have an equivalence relation twiddle on our set X if there exists a subset A in the Cartesian product of X cross X. Okay. So remember, Cartesian products give us ordered pairs. So let's just go over the definition of that again. So say A, B, such that A is an X and B is an X. Okay. The first Cartesian product you probably ever learned of was the real plane. That's the reals cross the reals. Okay. So remember, order matters in an ordered pair. Okay, so how A is defined is whenever A twiddles B, like little a twiddles little b, then the ordered pair A comma B is an element in A. Okay, and those are the only elements that are in A. Okay, all right. So, and the following statements are always true. Okay, so we have the same deal again. So we have reflexivity. So what was it before? Before we said, okay, if A is an X, then A twiddles itself. So what is what is that, but with this kind of speak? Well, if A is an element in X, then the ordered pair A comma A is in our set A, okay? All right, part 2, symmetry. All right, so same kind of deal. Before we said if A twiddles B, then B twiddles A. Well, A twiddling B, that means A comma B is in A. Okay, B twiddling A, that means that B comma A would be in A. And remember, these are not the same elements unless A equals B. So if A equals B, then this is the same as reflexivity. Well, it's not the same as reflexivity, but you're not saying anything new. Really, when symmetry is special is when A and B are not the same. If A equals B, then this is always true, because A comma A is an A, then A comma A is an A. Okay? Oh, and if that's confusing, the one I like to think about is if we go back to the real plane, you know that 0, 1 is different from 1, 0. Okay, one's a y-intercept, the other one's an x-intercept. They're different. Okay? All right, transitivity. Well, if A comma B and B comma C are both elements in A, which means that A twiddles B and B twiddles C, then A comma C is in A. So that means that A twiddles C. Okay, so whichever one makes more sense with your brain, grab a hold of it and just do it that way. But yeah, well, they're the same though. They're the same statements and so one of the reasons why I really wanted to kind of sink that in is that order does matter. Who's on what side of the twiddle does matter. I mean, you can see that from symmetry, right? So we wouldn't state that if that was just like always true or something. But yeah, whenever you have an equivalence relation, you should be able to flip it. It shouldn't matter what side of the equivalence relation you're on. But in order to show that a relation is an equivalence relation, you have to show that that's true. Okay. So a common question people have. Here, we're just going to do 2 notes. First, if you write A cross A instead of A, you are assuming part 2. Why you're assuming part 2 is because, well, if A comma B is in, so if the elements A and B are in A, capital A, sorry, I should have come up with different letters, then we do have the element A comma B and B comma A, because A and B are in capital A. Okay, so part 2 would always be true even if it wasn't an equivalence relation. So that's why that's why it's A instead of A cross A. And to some people that might be confusing, but a Cartesian product is a set, so you can have a subset that is also a Cartesian product. We just don't know what that Cartesian product looks like. Okay, so like, for example, R cross R, we write that as R squared. Or like, let's say I was going to pick some like R cross Z maybe. I don't know. And I just want to call it something different. I want to call it C, like the letter C. There's nothing stopping me doing that, right? But this C is still a Cartesian product. Its elements are still ordered pairs. All right. Okay, the second note I wanted to make, and I've been kind of hinting at this the whole time, but, words are hard. So I'm going to say you can easily define a relation. And remember, a relation always needs a set that it's relating elements on. Kind of like a function. Do you remember when we were talking about functions? And I said if you don't give a function a domain and a codomain, then it doesn't really make any sense. How am I supposed to know if it's a function or not? Okay. But I, and I make a relation and equivalence relation, which I'm going to often short to equiv rel. Okay. So I'm going to give one example, and then next video I'm going to talk about something different, and then the third video will be a whole slew of examples. Okay? All right. So this example, define a relation twiddle on the reals such that x twiddles y if x is less than y, strictly. Let's see what properties twiddle has on R, on the reals. Okay? So first we want to check reflexivity. Okay? So if x is in the reals, well, bummer. If it was reflexive, that would mean that x would twiddle x. But that would mean that x is less than x, which is not true. So let's put it this way, that x equals x. So x is not less than x, meaning, and so you don't always have to write all these words, but I'm writing these because this is the first time you've seen something like this. Well, probably, maybe not. Okay, meaning x does not twiddle itself. So twiddle, not reflexive. Okay, now if we were trying to show that twiddle is not an equivalence relation, this is enough. Check. Because an equivalence relation has to have all three. It has to have 1, 2, and 3. And we already showed it doesn't have 1. Okay, so we'd be done. But I want to show you how this process works for all of them. Okay, so we're going to keep going. And it just kind of, my question was very vague. I just said, let's see what properties twiddle has on the reals. Now, could you define twiddle on some other set? And maybe it would be an equivalence relation. Maybe. You'd have to see. I mean, I think it's going to be hard to get something to twiddle itself when it's going to equal itself. But anyway. Okay. Part 2. If x twiddles, let's say y. Okay. This means x is less than y. Okay, so now I'm hoping you're seeing why it's important what order they're in, right? Because we do know that less than, it does matter who's on what side of a less than symbol. Then x is not greater than y. So y does not twiddle x. Right? Because another way to write this is y is not less than x. Right? So twiddle, not symmetric. I also shorten those words a lot. I'm all about shortening how much I need to write. Which may not seem obvious from the way that I write proofs, but okay. If x twiddles y and y twiddles, I don't know, z, this means x is less than y and y is less than z. Okay, so x is less than y, it's less than z, okay? And it might be tempting, it might have been tempting to just have jumped right to x is less than z, but we need to show this part. So this gives that twiddle is transitive. All right. So notice, okay, I did say you could write less words than I wrote, but that doesn't mean that it's just bare bones. So you don't just say not reflexive, not symmetric, transitive. Okay, if you just made a list like that, probably wouldn't get you much points. Okay, but if you did write something like not reflexive because blah blah blah, so you still need to give reasoning. And so remember, when we're trying to show, so if a relation was reflexive, that means for all elements in its set, it's reflexive, okay? That those elements each twiddle themselves. So to contradict or to prove a for all statement false, all you need is one example. So what you could have done is you could have said 0 is in the reals. 0 is not less than 0. Therefore, 0 doesn't twiddle 0, so twiddle, not reflexive. Okay? Not the case when you're trying to prove a for all statement is true. Okay, so for part C, we couldn't have just picked out 0, 1, and 2 and been like, well, 2 is bigger than 0. That's not going to work out, right? Because we want to show it for every single one. So sure, maybe it works for 0, 1, and 2, but maybe it doesn't work for, I don't know, a gajillion, 10, and negative 34. Okay? So you always... so when trying to prove a for all statement true, you need to show for all. But in this case, actually, we were able to show that for all elements in R, it's not reflexive. And whenever x twiddles y for a generic x and y, they are not, y does not twiddle x. So this is kind of special. You're not always going to be able to show that. Okay? And sometimes you will come across questions that will use these parentheses like I did up here. Okay? And they'll just give you a list of what the equivalence relation does. So they'll give you a set with like maybe just like 4 elements in it. And it'll give you a relation. It'll say what the relations are on it with these parentheses. Okay, and then you just go through the parentheses. You make sure does everybody twiddle themselves. For every A in our set, do I have A comma A? Okay, and then every time I have A comma B, do I also have a B comma A? All right, whenever I have B as the second in the ordered pair, and also another relation that has B as the first, okay, for any B of the ordered pair, am I able to take the first from this one and the second from this one, and do I have a relation that looks like that? So if I have A comma B and somewhere else I have a B comma C, do I have an A comma C somewhere else? Okay, so that's how you do those ones. Maybe I'll give you an example of those in my 3rd video. Okay, have a good one. Bye.